So lesson 8, this is the last lesson in chapter 4, is going to be about applying these trig functions. So using them for real life problems, making models using the trig functions. So first off, something we need to talk about is breaking down degrees into minutes and seconds. So right here you can see this says cosine of 5 degrees. This is 40 minutes. That's how you'd say that when you see it with the degree, 40 minutes, and this is 12 seconds. So what a minute is essentially a 60th of a degree. So if you could take 1 degree and cut it into 60 pieces, that would be, each of those would be a minute. And if you could take those and cut them down into 60 pieces each, that would be a second. So this is a way just to be more precise with degree measure, because there's obviously something between 5 degrees and 6 degrees. 5.5 degrees would be 5 degrees and 30 minutes. So we can use this right here to get a more precise number for degrees. So first we need to look at how to convert minutes and seconds into a degree measure, and then we'll find the cosine of it. All right. So what you want to do is take the number of minutes, all right, and divide it by 60, and then take the number of seconds and divide it by 3,600, because each minute is a 60th of a degree, and each second is really a 3,600th of a degree, because each second is a 60th of each minute. So whenever we add these to 5 degrees, we get a decimal representation for the degrees. All right, so 40 over 60 is 0.66666, and then we add that to 12 over 3,600, and it gives us 0.67. And we add that to 5, so you get 5.67. So this is really telling us to take the cosine of 5.67 degrees. And then, of course, at this point, we can use our calculator, make sure the mode is in degrees. So hit mode. We've got it in degrees. That's good. So we can hit cosine of 5.67, and we get the answer of 0.995. All right. So that's how you use minutes and seconds to figure out a decimal representation for your degree. So you guys try this one down here. Should be pretty basic, but give this one a try and I'll go over it. All right, so you can see right here we do 30 over 60 and the 45 seconds over 3,600. We get the decimals 0.5 and 0.0125. Add them to 20 and you get 20.5125. Then you take the sine of that and get 0.35. All right, so we just needed to talk about how to do this because one of our application problems later is going to involve minutes and seconds. So just needed to make sure we understand how to do that first. So let's look first at this problem. Safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees and a fire department's longest ladder is 110 feet. We want to know what is the maximum safe rescue height. So imagine you've got a building and you've got some ladder that has to come up to the building somewhere, right? And they tell us this ladder is 110 feet long and the angle of elevation for the ladder is 72 degrees. And we want to know what's the maximum safe rescue height, the maximum height that ladder can reach. So we're going to call that side X. All right, so what we got to do is use our trig functions. We got to remember SOHCAHTOA. So the sides that we're using X, which is the opposite from our angle, and 110 is our hypotenuse. So O and H comes from So we're going to use the sine function. So we're going to say, what's the sine of 72 degrees? That should be the opposite, which is X over 110. All right, now you just solve for X, you just times it by 110. And over here, you got to, of course, times by 110. So over on the right, we get X equals, and we type in our calculator 110 times sine of 72. Again, make sure that mode is in degrees. All right, if mode's not degrees, you need to change it. So we're going to hit 110 times sine of 72, and our answer is 104.6. So our maximum height is 104.6 feet. That's the highest that ladder is going to be able to reach, which is important for a fireman to know if they've got to rescue somebody. If the ladder's even got to reach, no point wasting time trying to get there if the window or whatever is too high up. All right, so do this problem down here. It's similar. So try it, and I'll go over it. House, and the ladder's 20 feet long, leaning against the side of the house at an angle of elevation of 80 degrees. What's the height from the top of the ladder to the ground? So we set up the problem exactly the same as the last one, and we have to times 20 to get x by itself. So 20 times sine of 80 is 19.7 feet. Let me know if you have any questions or didn't get that one right. All right, so let's look at another problem. So we've got a building. This one's a little bit more complicated. You've got a building that has a smokestack coming out of its roof. All right, so let's draw that real quick just to give us something to start with. Building, there's a smokestack right here coming out of the roof. All right, and it says that at a point 200 feet from the base of the building, the angle of elevation to the bottom of the smokestack is 35 degrees. So let's go out here 200 feet from the base of the building. It says the angle of elevation to the bottom of the smokestack is 35 degrees. And the angle of elevation to the top is 53 degrees. So from that same spot, looking up to the top, that angle, we'll put it in red, is 53 degrees. Alright, so we've got two triangles made this time. We want to find the length of the smokestack from its base to the top. So what we're looking for is really the distance from the length of the smokestack, okay, from the top to the bottom. So what we've got to do is find from the ground to the top, right? We'll call that Y. And then we need to find from the ground to the bottom, we'll call that Z. And then we can subtract, right? We can do Y minus Z, and that'll leave us with X. So we're going to do two equations this time. One using Z and one using Y. So let's do the small triangle first, the one with Z. So now we're just looking at this triangle right here. All right, so we've got the 35 degrees. Z is opposite. All right. And then 200, that's adjacent, right? It's not the hypotenuse now. So we're going to use the trig function that uses opposite and adjacent, which is tangent, TOA, right? So we're going to do the tangent of 35 degrees, which should equal the opposite Z over the adjacent 200. So now we're going to multiply by 200. So we get Z equals 200 times the tangent of 35 is 140.04. Yeah, 140.04. All right, now let's figure out what Y is. So looking at the bigger triangle now, okay, this red one. All right, so we're still going to use tangent because Y is still the opposite for this triangle, and 200 is still the adjacent. So we're still doing tangent, but now we're doing tangent of 53 degrees equals the opposite Y over the adjacent 200. Solve the same way, times by 200, times by 200. So we're going to get Y equals 200 times the tangent of 53 this time. It's 265.4. Alright, so the distance from the bottom of the ground to the top of the smokestack is 265.4. And the distance from the bottom of the smokestack to the ground is 140.04. So we subtract those, and it'll give us the height of the smokestack. You subtract those, and you should get 125.36. Okay, so the height of the smokestack X is about 125.36 feet. That's how tall it is. All right, so that's a way to measure the height of the smokestack without having to go up there and climb it and actually, measure it directly. You can use indirect measurement like this to figure out how tall it is. So you guys go ahead and try the problem down here. It's a very similar problem, and I'll go over in a second and see if you got it right. So on this problem, you actually had to use your knowledge of minutes, okay, because they tell you that the distance from the, first of all, they tell you the distance from a point of a church is 50 feet, and you're looking up at this church to the base of a steeple. Now, the steeple's the part of the church that sticks out at the top. It's just kind of protrudes up from the top of the building. So the angle of elevation from to the base of the steeple and the top of the steeple are 35 degrees and 47 degrees, 40 minutes respectively. Now, if you've never learned how this respectively thing works with, writing, respectively just means whatever I told you first, in this case, the elevation to the base, and then I told you elevation to the top, use those same orders for the numbers I give you. So the base is the first one, so 35 degrees is the angle of elevation to the base. And then to the top of the steeple is 47 degrees and 40 minutes. All right, so what we need to do is convert 47 degrees and 40 minutes into just degrees. So whenever we do that, we take 40 and divide it by 60, get 0.66666, add that to 47 to get this. Now what I did is I converted that to a fraction just to be exact because I don't want to have to round. So I made that into a fraction, 143 over 3. All right, so I use that value for my angle as opposed to a degree measured with a decimal. So right here I did then the tangent for the large red triangle. I did the tangent of 143 over 3 degrees equals z, where z is this distance from the ground to the top of the steeple, over 50. And of course it's tangent because that's the opposite side of the angle and 50 is the adjacent side of the angle. So then I times by 50 on both sides. And whenever I type in 50 times tangent of 143, I get 54.89. All right, so I just rounded it to the hundredths. Then we do the same thing with the smaller black triangle. So I do tangent of 35 equals y over 50, and I times by 50, and I get 35.01. So the distance from the ground to the base of the steeple is 35 feet, essentially, and the distance from the ground to the top of the steeple is about 55 feet, essentially. So I subtract those two numbers to figure out how tall is the steeple, find the actual height of the steeple. So I subtract 54.89 minus 35.01, and I get 19.88 feet. So that's how tall the steeple is from its base to the tip up here. All right, so now let's move on. Look at a new type of problem. So it says a swimming pool is 20 meters long and 12 meters wide. The bottom of the pool is slanted such that the water depth is 1.3 meters at the shallow end and 4 meters at the deep end. We want to find the angle of depression of the bottom of the pool. Okay, so we're looking at angle of depression now instead of elevation. That's an angle where you drop down as opposed to an angle where you go up. So let's draw this real quick. We've got a pool. We're going to kind of draw like a side angle view of it. All right, it tells me the shallow end, and it's got a shallow end and a deep end. And it says the shallow end is 1.3 meters, and the deep end is 4 meters. All right, and we want to figure out what is the angle of depression of the bottom of the pool. It tells me that the pool is 20 meters long, right, and it's 12 meters wide. Now, the 12 meters isn't really important information. What's important is that it's 20 meters long. And if you've not been around pools a whole lot, the length of a pool goes from the shallow end to the deep end. Okay, so we're not really worried about how wide it is. That's not important information, but we know it goes from 1.3 meters down as deep as 4 meters. Okay, so what we're looking for is, if you can imagine a dotted line straight across here, we're looking for this angle. Okay, I'm going to put a theta in there. So we're looking for this angle in here. What's the angle of depression to drop down? Okay, if I was making, this pool, what kind of angle would I have to put that on to drop it down from 1.3 meters to 4 meters? All right, so what we want to figure out then is how long is this right here? All right, well, essentially that's just the deep end minus the shallow end. So 4 minus 1.3 makes this 2.7, right? 4 is the entire depth. You take away the shallow end that would be about right here, and that gives you 2.7 left. So now looking at this triangle that we've got, all right, we've got this side's 2.7, and we know the length all the way across the top is 20 because it's of course the same length as the pool was. So we can set up a trig function now, but now the unknown is our angle as opposed to being one of our sides. So 2.7 is the opposite of our angle, and 20 is the adjacent side, right? Of course, the side on the bottom, the slant, is our hypotenuse. So we're going to use tangent. Tangent of theta equals opposite, which is 2.7, over adjacent, which is 20. Now, to solve for tangent, or solve for theta when we have tangent, all right, you're going to use a button on the calculator to cancel tangent. So we've got to cancel tangent to leave the theta by itself. Well, to cancel tangent, you're going to use what's called arctangent. All right, and you can see it right here in blue above the tangent button. It's tangent with a -1. Okay, so that is what cancels tangent. So we do arctangent of both sides. That's going to give us arctangent of 2.7 over 20, which will give us our answer. So to cancel the tangent right here, we do, all right, we're going to do arctangent of this, and it'll cancel. And I'll just leave theta, but of course if we do it to the left, we've got to do it to the right. So we do arctangent of 2.7 over 20. And that gives us our angle. Of course, the mode is set in degrees, so that's a degree measure, 7.69 degrees roughly. Right, so that's the degree slope that pool needs to be made at in order to make sure that those, those values are right for the depth and the length of the pool and everything. All right, so let's go ahead and practice this next problem. And it should be one where you have to find the angle. All right, notice there's a hint right here, so don't forget that hint. Give it a try, let me know if you need help. All right, so here's a kind of a picture of this example. So you've got a ship that's 2.5 miles offshore, and the lighthouse is 250 feet tall. We're going to figure out what's the angle of depression from the lighthouse looking down at the ship. So obviously, this angle of depression, right, is not really in the triangle at the bottom. So we want to try to use the triangle that's up here at the top, this imaginary triangle. So we've got, this is still 250, so we can kind of transfer the numbers over here for this other triangle. And the distance from the ship offshore is 2.5 miles. Now, we need to convert that to feet, right, because our height of our lighthouse is in feet. So we gave our hint that 1 mile is 5,280 feet. So 2.5 miles is going to be 13,200 feet. So this length is 13,200 if we convert those miles into feet. So now, which trig function do we need? Well, 250 is the opposite side from our angle, and 13,200 is the adjacent side. So opposite and adjacent is tangent. So we do tangent of theta again equals the opposite 250 over the adjacent 13,200. To get rid of tangent, we do arctangent. That cancels and leaves theta. If we do arctangent over there, we need to do arctangent to the other side. So arctangent of 250 over 13,200. And we type that in the calculator. And you should get 1.09. 1.09 degrees, which makes sense because that boat's a long ways away, right? It's a long ways away from this this lighthouse, so the angle is going to be very, very small to have to look down to get to that boat. All right. So let's move on. Last kind of problem we need to work on. All right. So in order to do this problem, first of all, you need to be familiar with the concept of a bearing. So you'll hear, in aviation, navigational time, the back bearing, north, whatever, blah, blah, blah. So they use this terminology, and you need to be aware of it when you see some of these problems. So if we imagine a compass, right, north, east, south, west, okay, if I said that your bearing was south 35 degrees east, all right, so south 35 degrees east. What that means is first look at the south part of the compass. You're going south, but then you're going 35 degrees from there in the direction of east. Okay, so that's what south 35 degrees east means. Okay, just another one, north 80 degrees west. So we're going to go north, right? But then we go 80 degrees west, which is almost all the way west, right? So that would be in this direction right here, because west is over here. Okay, then just one more, north 45 degrees east. All right, so this is north 45 degrees east, of course east is over here, and 45 is about halfway, right? Because it's 90 degrees to go from north to east to be 90 degrees, so 45 will be about midway. So that's just how bearings work, and we need to be able to understand that to do this next problem. So it tells us that a ship leaves port at noon and heads due west at 20 knots. A knot is a speed that is used in navigation on oceans, and all it really means is nautical miles per hour. Okay, so you can think of it as like miles per hour, but it's nautical miles per hour, and you'll hear it called knots. It's a little bit different than miles per hour. So a ship leaves port at noon and heads due west. So let me draw a ship here. Okay, doesn't be perfect, and we go west, and it says that we go 20 nautical miles per hour. Now at 2 p.m. Now at this point we should stop and think. Okay, at 2 p.m. we left at noon, and that's now 2 p.m. So we've been traveling for 2 hours at 20 knots per hour, right? 20 nautical miles per hour. So how far have we gone? Well, if we went 20 per hour and we just traveled for 2 hours, that's 40. So we've gone 40 up to this point, right? 20 times 2. So we can label that right there as 40, and I'll just put NM for nautical miles. Right, now it says the ship changes course to north 54 degrees west. So think about our bearing now. If we go north, straight up north, and then west 54 degrees. So right here's north, and this is 54 degrees going towards the direction west, right? So we go north 54 degrees west, and it wants to find the ship's bearing and distance from the port of departure at 3 p.m. So now that means we travel another hour, right? So another hour is going to be 20 more nautical miles along that line. And what they want us to do is find the ship's bearing and distance from the port of departure. So how far are we now from where we started? And also, what is the bearing that that line would be on? All right, so let's define right here. So let's go ahead and make this into a triangle, okay, a right triangle. So I'm going to draw this line down and across. All right, so what we know is this is 40, this one is of course 20. We want to find the distance of that red line right there. So what we can use is this small right triangle that we have right here. We can use our knowledge of trig to find the other two sides of this triangle. We know that the blue side is 20, and we need to figure out what are the other two sides. So let's call one side, it doesn't matter, we can call one side X and one side Y. Alright, so we know that this bearing measures 54. Well, if it's 54 from here to here, it's got to be 90 all the way down. So this other angle down here has to be 36. Right? So now we can use that with the 20 to find X and Y. So to find X is opposite 36. So we would do sine, because X is opposite, 20 is the hypotenuse, right? Because here's your right angle. And then over here we have the adjacent side is Y. So sine of 36 degrees is going to be X over 20. All right, and we do times 20 times 20. So X is going to equal 20 times the sine of 36. You get 11.756. I'm going to be a little bit more precise on this one because we're dealing with a lot of different numbers. All right, now to find Y, Y is the adjacent side, so we need to use the cosine. So we're going to say cosine of 36 degrees should equal Y over 20. Adjacent over hypotenuse. Then times 20 times 20. So Y is going to be 20 times the cosine of 36. 16.180. And again, that's going to be in nautical miles. So now we know this is 11.756 and Y is 16.180. So at this point, you can use this valuable information to figure out the length of the hypotenuse. A couple different ways. So one way that we can do that is by using Pythagorean theorem, because we know the two legs of the right triangle, so we can just do 11.756 squared plus 40 plus 16.180 squared, and everything to find the red line. But we've got to find the bearing anyway. So let's find the bearing first, and then we can use it to find the length from where we are now to where we started. So to find the bearing, we need to find the measure of this angle theta. Well, now we know the opposite side of that is 11.756, and the adjacent side for that angle is 40 plus 16.180. So we can use a tangent function. Tangent of theta is going to equal 11.756, which was the sine of, 20 times the sine of 36 over, and now the long leg is 16.18, which was 20 cosine of 36 plus the 40 that we've already got. So it's hard to read, that's a little small. 20 cosine 36 plus 40. So we can type it in just like that, and that'll give us our most exact answer. So let's look right here. We do second tangent of 20 times the sine of 36, and then divide that. And on the bottom, we need to put this in parentheses because we're adding those two. So hit 20 cosine 36 plus 40, and then close that parenthesis. And you have to close another one, and it gives us 11.81 degrees. Okay, so theta is 11.81 degrees. So then our bearing, okay, remember bearing starts north. So north, and then however far we have to go to get to that value. So we need to subtract 11.81 from 90. So our bearing is actually north, and then subtract 11.81 from 90, and you're going to get 78.19 degrees west. All right, so there's our bearing. That's the first answer. All right, now we can use this value, 11.81, along with 11.756 to find our distance that we are from where we started. So that would be opposite and hypotenuse. So we can say the sine of 11.81 equals the sine, 11.756 over z. Of course, we times by z, whenever we got z on the bottom, okay, when you got z on the bottom instead of on the top, you got to swap it with this. So we're going to swap those, and we type in 11.756 divided by the sine of 11.1, or 20 sine of 36 divided by the sine of, divided by, sine of 11.81, if we round it off. So 57.43, and that's, of course, nautical miles. So that's the distance that we traveled from where we started. That's how far we are from where we started. All right, so a lot to that problem. I know there's a lot to it. Give this next one a try, see if you can figure it out, and I'll go over it. All right, so this problem's a lot more simple than the one that I just did. So it tells us that a ship leaves port at noon and has a bearing of south, 29 degrees west. So there's our boat up here. We've got it going south and then 29 degrees bearing to the west. The ship sails at 20 knots, and we want to know how many nautical miles south and how many nautical miles west does the ship travel by 6 p.m. So if it goes that direction until 6 p.m., that's 6 hours later if it left at noon. So going 20 knots, it went 20 knots each hour times 6 is 120. So it's 120 nautical miles from where it started. So that's what this line represents right here. The boat is now here where it started, up where you got the red circle up there. So it's gone 120 nautical miles at a bearing of south 29 degrees west, and we want to know how far is it south from where it started and how far is it west from where it started. So that's what we need to find here, x and y. Those represent how far south and west it's traveled. So we can do that very easily using trig functions. 29 degrees if we want to find x, x is the opposite. Of course, y is adjacent, and this is our 90-degree angle, so 120 is the hypotenuse. So we can use sine to find x. The sine of 29 is going to equal x over 120. Just multiply by 120, multiply by 120. So x is going to equal 120 times the sine of 29. $58.17. Let me say 58.18. And that is nautical miles. So it's 58.18 nautical miles west. All right, and then let's find y. So y is the adjacent, so we're going to use cosine of 29 degrees equals y, which is the opposite over the hypotenuse, which is 120, times 120 times 120. So we get 120 times cosine of 29 is 104.95. So we are 58.18 nautical miles west and 104.95 nautical miles south from where we started. All right, so that's how you do these. You've got practice problems on the first slide. So let me know if you need help on these, and appreciate your all's attention.